Hi, let's learn about free body diagrams. So, a free body diagram is simply a way of simplifying a graphic representation of the various forces that act on an object. And the point of it is, by using this visual representation, we can quickly get a sense of which of the forces acting on an object are balanced and therefore don't cause it to accelerate, and which of those forces acting on it are unbalanced and will cause it to accelerate. So, we should be able to use it to figure out how fast and which way the object should accelerate. And it's a very, very powerful tool that we'll use a ton this year. Okay, so when we do a free body diagram, there's a couple rules we got to follow. Take the object, whatever it is. Don't worry about trying to draw the object. So it's a car, a person. Don't worry about that. You simply draw a dot that represents the object. And then you're going to draw forces that are acting on the object. And each of the forces acting on the object will be drawn as a line that extends in the direction of the force with an arrow pointing in the direction of the force. The length of the line will represent the relative magnitude of the force. So, for instance, in this case here, I have 1,000 newtons of force pointing to the right. And I have a 500 Newton force pointing down. So therefore, the length of the 500 Newton force needs to be represented as having half as long as the one for the 1,000 Newton force. And that's a very important thing. You'll notice in FRQs when they have you draw free body diagrams, which they will give you a grid. And it's important that you follow that rule of making sure that the arrow is scaled appropriately to relative to the other forces acting on the object. The other thing that's worth noting is you never have an arrow coming to it. So if we said a person is pushing an object like a car to the right with 1,000 newtons of force, I would draw it this way. I would not draw it this way with an arrow pointing towards the thing that's being moved. You always have the arrows originating with the object and pointing away from it in whichever direction the force is acting. So here's this man. Okay, so a man pushes a 50-kilogram crate across the floor by applying 300 newtons of force to the right. There's a force of friction between the crate and the floor is 100 newtons. Okay, so now remember, I'm going to draw a dot. Now, the 300 Newton force is going to be represented starting from the object moving outwards. I'm not going to draw it coming towards it. I know it looks that way when you look at a picture, but when you draw a free body diagram, you say, here's the object. A 300 Newton applied force is pushing it this way. So I'm going to scale it by going 1, 2, 3. And so each line represents 100 newtons. I'm going to label it FA, meaning applied force. Now, it's a 50-kilogram crate, so mg is going to be 500 because g is 10. So I'm going to have 500 newtons of force acting in the downward direction on the object. So that line is 5 tick marks long. I'm going to label it mg to mean gravity. Now, the object is not sinking through the floor, so we can assume there's a 500 Newton upward normal force from the floor. So I'm going to draw that one going up. And now, and also I've been told there's a 100 Newton force of friction. And remember, friction is always going to act counter to the direction of motion. So I'm going to draw that 100 Newton force going the opposite way. And the value of doing this is I can now look at this and I can see these two forces are balanced. They're pointing opposite directions of the same magnitude. They have no bearing on the motion of the object. What does have a bearing on the motion of the object is the 300 Newton force going this way and the 100 Newton force going that way. And if I was to use the tip-to-tail method of resolving the vectors, I would go 300 this way, 100 this way, and I'd see my resultant vector would be 200 newtons to the right. And based on that, I should be able to figure out the acceleration of the object. I need to move my face out of there. How do I move my face? There it is. Okay, and that's what I would get for my acceleration. All right, let's move on to the next slide. Okay, now let's try an elevator problem. I love my elevator problems. See, I'm going to move my face out of the way. All right, so I've got a person, an 80-kilogram person standing in an elevator, and the elevator is accelerating upwards at 2 meters per second, and I want to draw a free body diagram representing the forces acting on the person. So remember, forces are always about objects. Okay, now these objects can be part of a system, but each object in that system is going to have its own free body diagram. So for this person, I'm going to say this dot represents the person. There is gravity is always going to be pulling down on objects that are near the Earth's surface. So I've got mg is going to be 800 newtons. Now in this case, my grid was such that I'm going to say, well, I'm going to make each of these equal to 200. So 2, 4, 6. So 4 of those makes 800. And so if he's accelerating upwards, clearly the normal force must be greater than the gravitational force, otherwise he would not accelerate. So before I can draw this force here, I'm going to have to figure that out using Newton's second law. So I'm going to say the sum of the forces acting on this person is going to equal the person's mass times the person's acceleration. Now I know that mg for the person is 800. What I don't know is what the normal force is. Now it's going to be negative 800 because I'm setting down as the negative direction. So therefore up is the positive direction. And the person has a mass of 80 kilogram and is accelerating in the positive direction at 2. So when I resolve this, what I'll get is 2 times 80 plus 800 is going to give me 960. So I'm going to then draw that arrow, 2, 4, 6, 8, and not quite 10 tick marks. Okay, so it says that's 690. All right, let's try this one. So I have a 2 kilogram ball traveling upwards through the air at 8 meters per second while encountering 6 newtons of friction force. You got to be very careful. College boards will do this to you a lot of times. This right here, velocities, they're not part of a free body diagram. A free body diagram only represents the forces acting on it, not the motion of the object, only the forces. So I'm going to draw a dot representing a 2 kilogram ball. Here it is. mg is going to be acting on it. So 2 times 10 is 20. So I have 20 newtons of downward force. And in this case, I'm just going to set down. I mean, I could, we could make it negative 20, or I could set down as the positive direction. Let's say I set down as the positive direction here. So therefore, the frictional force is going to be negative 6. So it's going to be 6 in the same direction. So in this case, I did 5, 10, 15, 20. So this one's going to be a little bit more than 6, pointing in the same direction. Notice, so I had to make my dot a little bit bigger so I could accommodate 2 forces acting in the same direction on the same object. But there's no other forces acting on this object. So therefore, I would just say, if I want to know what the ball's acceleration is, now I've got to decide what I want to put as up or down. To be honest, when I made this slide, I don't remember which I did. So we're going to say the sum of the forces equals ma. I chose down to be the negative direction, which we often do. All right, so I'd say negative 20 plus negative 6 equals an acceleration, a mass of 2, and I'm going to find the acceleration. And what was it? I get negative 13 meters per second squared, which makes sense. This ball is going to slow down faster than it would if there was no friction. So it's moving upwards, but it's slowing down at negative 13 meters per second squared. I think I have one more here. Okay, so here's what I got. I have a box of mass m being pushed across a floor. While encountering friction, force that's equal to 1/2 mg. I want to draw a free body diagram for each one of these. So I have a box that's accelerating to the right as a result of this. So this line represents mg. I don't know what m is, so I just, all that matters is that this one is the same length as this one. But we don't always get numbers. And I'm going to have an applied force going this way. And since it is accelerating to the right, what I know is the friction force has to be less than that. A box is moved to the right at constant speed. It's not accelerating. Net force is 0. Therefore, in addition to the gravitational and normal forces being equal, that means that the applied force and the friction force have to be equal. I meant to draw these equal. It looks like this one's a little bit longer. It's not supposed to be. They're supposed to be the same length. And in fact, I should have kept it consistent and made it the same length as that one. I drew it on different days, sorry. All right, and the box is slowing down as it continues to move to the right. The person stopped pushing it, so the applied force is no longer there, but the friction force is still there. So I would see that my normal force and gravitational force are balanced. There's no longer an applied force, and so there's now a frictional force acting against it. Remember, I do not draw any arrows representing motion or velocity, only forces. All right, thanks for watching this.